friends, this is Dr. Siva Nagaraju from IARE. Today we are going to discuss pulse modulation and types of pulse modulation, and again PAM, pulse amplitude modulation, and how to generate and demodulation. So these are the topics we are going to discuss in this session. So first, before going to pulse modulation, first, what is modulation? Already know the definition of the modulation. So some parameter of sensory carrier is varied continuously in accordance with the message signal, we can call as modulation. Whereas in analog communication, we can know this definition very well. And again, in pulse modulation, some parameter of pulse strength is varied in accordance with the message signal. So what is the difference between continuous wave modulation and pulse modulation is the carrier. Whereas in continuous wave modulation, the carrier is continuous, sensory continuous varying signal. Whereas in pulse modulation, the carrier is pulse. So that is the difference between continuous and pulse. And now the types of pulse modulation. So having two varieties. One is analog pulse modulation and another one is digital pulse modulation. So in analog pulse modulation, a periodic pulse strength is used as the carrier wave, what we discussed earlier. And some characteristic feature of the each pulse, like amplitude, duration, or pulse, is varied in a continuous manner in accordance with the corresponding sample value of the message signal. Thus, in analog pulse modulation, information is transmitted basically in analog form. Now, there are two types of analog pulse modulation systems. We have one is pulse amplitude modulation, PAM. So this is a basic one. And the second one is pulse time modulation. So first we are going to do a brief discussion about this PAM. In pulse amplitude modulation, the amplitude of the pulses of the carrier pulse strength is varied in accordance with the modulating signal. Again, in pulse time modulation, the timing of the pulses of the carrier pulse strength is varied. So again, this PTM can be classified into two varieties. One is pulse width modulation and another one is pulse position modulation. So in the next two sessions, we are going to discuss about pulse width and pulse position modulation. So basically in pulse width modulation, the width of the pulses of the carrier pulse strength is varied in accordance with the modulating signal. So the difference here in a pulse amplitude modulation, the amplitude of the pulse of the carrier pulse strength is varied, whereas in pulse width, the width of the pulses of the carrier pulse strength is varied in accordance with the modulating signal. Whereas in PPM, the position of the pulses of the carrier pulse strength is varied. So simply you can say the amplitude of the pulse is varied, we can call it as pulse amplitude. The width of the pulse is varied, we can say that pulse width modulation. The position of the pulse is varied, we can call it as PPM. Now we are entering for the digital pulse modulation. So on the other hand, the message signal is represented in a form that is discrete in both time and amplitude, thereby permitting its transmission in digital form as a sequence of coded pulses. So the example for digital pulse modulation is PCM, pulse code modulation. Whereas in analog pulse modulation, we're having three varieties. One is PAM, second one is PWM, and third one is PPM. But whereas in a digital pulse modulation, we're having only one is a pulse code modulation. So when I'm entering to the PCM, first we could describe the sampling process. So in any pulse modulation systems, the basic one is sampling process. So you know that why we're going to the sampling. Why? Because the message signal is in continuous form. We are going to convert these continuous time signals into discrete time signals by applying the sampling. So sampling is done according to sampling theorem. So by describing the sampling process, which is basic to all pulse modulation systems, this is followed by a discussion of pulse amplitude modulation, which is the simplest form of analog pulse modulation. Why? Because in analog pulse modulation, we're having only sampling. When you enter into the digital pulse, after sampling, you can use the quantization. Then after go for the encoding. So, three operations is done in digital pulse modulation. One is sampling, second is quantization, and third one is the encoding process. So after doing these three processes, the analog signal, which is going to convert into digital one. But in analog pulse modulation, only single process, that is a sampling process. Here, the message in time domain only, it is discrete form. After applying sampling process, the continuous message signal is converted into discrete only in time domain, but not in amplitude. Okay. So now first PAM, pulse amplitude generation. So this is the first analog pulse modulation scheme. So in PAM, the amplitude of the pulse carrier varies proportional to the instantaneous amplitude of the message signal. So it is general, the definition of the modulation. So you know the definition of the modulation. Some of the characteristic of the carrier signal is varied in accordance with the instantaneous value of the message signal. So that is for modulation definition for an analog form. But here this is in pulse. So the amplitude of the pulse carrier varies proportional to the instantaneous amplitude of the message signal. So in fact, the pulses in a PAM signal may be a flat top, natural, or ideal type. So having three varieties of sampling is done. So depending on the sampling, the name is coming for the PAM. So this is a natural PAM. This is the figure for natural PAM. So here we're having pulse form is there, and sinusoidal waveform is also appearing in this waveform. So this is a natural PAM. That means we are here, the sampling is done in natural. So that is natural PAM. And this is a flat top PAM. So here you can see the pulses having flat edges at the top of the pulse. Flat edges at the top of the pulse. But generally we use flat top PAM frequently than other than natural and ideal sampling. So here we can see this is ideal sampling. So after ideal sampling, getting ideal PAM. Ideal PAM. So here the impulses, the blue one is the impulse responses, and the sinusoidal wave is the message signal, which is going to discrete in the time domain here the x-axis we're having t, and here this is amplitude in y-axis. So after applying the sampling theorem or sampling process, the continuous wave message signal, which is going to discrete. So here having instance 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, like this. So this instance it is going to discrete. Why? Because in continuous you can say it is a infinite number, but here after sampling it is going to discrete and finite number. Discrete means finite, so it is a countable number. So here in this picture we can visible three types of samplings. First one is ideal sampling, so it is impulses and natural sampling. Second one is, and third one is flat top sampling. So here we're having three varieties of sampling. Now the circuit diagram, how to generate pulse amplitude modulation. So out of these three pulse amplitude modulation methods, the flat top is most popular and widely used. So we can see earlierly three varieties: ideal, natural, and flat top. So here we are going to generate the flat top pulse amplitude modulation. So in this circuit diagram, we're having two FETs and one capacitor. So the first FET Z1 having the gate that is acts as an ideal switch, and second FET which acts as a discharge switch. And M of T is the message signal and S of T is the PAM generator signal. Now we can see the working principle of this pulse amplitude modulation. So the sampling switch is closed for a short duration by a short pulse applied to the gate Z1 of the transistor. So here you can say G1 is there. So for this G1 we are giving a short pulse. A short pulse. After giving a short pulse, this capacitor is going to charge. Why? The switch is going to close. The sampling switch is going to close. So that's why here the M of T is entered into the circuit. So during this period, the capacitor C is quickly charged up to a voltage equal to the instantaneous sample value of the incoming signal M of T. Now the sampling switch is open and the capacitor C holds the charge. The discharge switch, the second FET, which acts as a discharge switch. So the discharge switch is then closed by a pulse applied to a gate Z2 of the other transistor. So due to this, the capacitor C is discharged to 0 volts. The discharge switch is then open and thus capacitor has no voltage. So here you can see the pictures. Here X of T is nothing much or M of T message signal, and S of T what you have generated. So here you can see the instant sampling instance. So the signal is visible here, and H of T, and finally the G of T is the conversion of S of T and H of T. After generation, here we go to demodulation of PAM. So in this method, the received PAM signal is allowed to pass through a holding circuit and a LPF, low pass filter. So after generation, again you go to demodulate the pulse amplitude modulation. So for this, the received signal PAM, the received PAM signal is given to a holding circuit. After the output of the holding circuit is given to low pass filter, finally you get the demodulated signal. So what is the demodulated signal here? Again the message signal, what we use it to generate at the transmitter, and the receiver which is going to reconstruct the original message signal from the received signal. So the reverse operation which is going to done in the receiver. So here the circuit diagram, and previously this is the block diagram. So switch S is there, here given as a PAM input, pulse amplitude input, and capacitor C is there, finally the output. Okay. So the switch S is closed after the arrival of the pulse, and it is opened at the end of the pulse. So here you can see, again come back to this circuit. So the switch S is going to close, then the input of PAM signal can enter into the circuit. If S is open, it never enters into the circuit. Okay. So here the switch S is closed after the arrival of the pulse. So what is the pulse here? The input signal pulse amplitude modulation, and it is open at the end of the pulse. So after entering the pulse, the switch is again open. So in this way, the capacitor C is charged to the pulse amplitude value, and it holds this value during the interval between the two pulses. So after this, holding circuit output is smoothened in LPF. Why? Because here in the block diagram, after the holding circuit, we are having low pass filter. So the low pass filter which is going to smoothen this signal. So we are having again the original continuous wave message signal is going to appear. So this is the output of the holding circuit and LPF. Why? Because in the transmitter we are going to generate this flat top pulses. We are getting PAM. The PAM is in flat top. So here the holding circuit output is in flat edges of the pulses. So after getting this holding circuit output, the LPF which is going to smoothen. So why? Because here my message signal is M of t is continuous signal. So again I am going to bring back this continuous time signal by operating these two circuits. One is holding circuit, another one is the LPF circuit. Okay. So what are the applications of this pulse amplitude modulation? So PAM we can use in Ethernet communication signals, and PAM signals can be used in photobiology, and we can use the PAM as an electronic driver for LED light. So these are the applications of pulse amplitude modulation. Why? Because in pulse modulation, PAM is the basic one, and this PAM which is relates to the amplitude modulation. So this PAM is very noise sensitive. So it is sensitive to the noise effects. So this is the drawback of PAM, and how this drawback is going to overcome in a PWM and PPM. Okay, we can discuss in the next session for PWM and PPM. And again, you can see one problem regarding this pulse amplitude modulation. So, for a pulse amplitude modulated signal or pulse amplitude modulated transmission of voice signal having maximum frequency equal to FM is 3 kHz. Calculate the transmission bandwidth. It is given that the sampling frequency Fs, which is equal to 8 kHz, and the pulse duration is tau, which is equal to 0.1 Ts. So here we are going to calculate the transmission bandwidth. Transmission bandwidth. So first, what they given? The data. They given FM. They given FM as 3 kHz, and again for sampling frequency they given Fs as 8 kHz, and the pulse duration is 0.1 Ts. So this is a given data. So by using this given data, we are going to find the transmission bandwidth. Okay. So we are going to solve this problem. So we know that the sampling period Ts is expressed as Ts, which is equal to 1 by Fs. Ts equal to 1 by Fs. Why? Because already they given Fs. So what is the Fs value? 8 kHz. So 8 into 10 power 3. So 1 by 8, you know that there is 0.125 into 10 power minus 3 seconds. So this is the sampling period. So we are going to find the sampling period from sampling frequency. So Ts equal to 1 by Fs. So Ts is equal to, got 0.125 milliseconds. Again, we can rewrite this in microseconds also, that is 125 microseconds. This is my Ts. So, and they given another clue, that is tau. They given the tau value. So that is pulse duration. Pulse duration, which is equal to tau is equal to 0.1 Ts. They given as 0.1 Ts. So 0.1 into Ts is 125 microsecond. So you got 12.5 microseconds. This is my pulse duration. This is my pulse duration. So after knowing this pulse duration, I'm going to find transmission bandwidth. So we know that the transmission bandwidth for PAM, pulse amplitude modulation signal, is expressed as bandwidth greater than or equal to 1 by 2 tau. So this is the formula for transmission bandwidth for a PAM signal. So previously they asked calculate the transmission bandwidth. So that is a given data is sample frequency is Fs, which is equal to 8 kHz, and the pulse duration is 0.1. So here we are going to find this bandwidth. So the bandwidth greater than or equal to 1 by 2 tau. So already we find the tau. So here I am going to substitute this tau value 2 into 12.5 into 10 power minus 6. So which is greater than equal to, again. So in denominator I am having 10 power minus 6. So I can send into the numerator as 10 power 6, and here is 25. So here you can write 1 into 10 power 6 divided by 25. So after calculating, we get the bandwidth is greater than equal to 40 kilohertz. So this is my bandwidth. So for a given data, I am going to find the transmission bandwidth. So my bandwidth is 40 kilohertz. So once again, you can see this problem for a pulse amplitude modulated PAM transmission of Y signal having maximum frequency equal to FM is 3 kHz. Calculate the transmission bandwidth. So here the given data is sampling frequency Fs is 8 kHz and the pulse duration is tau is equal to 0.1 Ts. So first we are going to find this Ts. So that's why I am taking the sampling period. So the sampling period can be expressed in terms of sampling frequency. Why? Because time is inversely proportional to frequency. So Ts, which is equal to 1 by Fs, and which is equal to 1 by 8 kHz. The frequency is in 8 kHz. So I am going to substitute 8 into 10 power 3. Then I am going to calculate. So I am sending this in denominator 10 cube to the numerator. You get 10 to the power of minus 3. And 1 by 8 gives 0.125. So Ts is equal to 125 microseconds. But my aim is to find bandwidth. For the bandwidth, the formula is bandwidth which is greater than equal to 1 by 2 tau. So the given another data is tau. So tau is equal to 0.1 Ts. So tau is equal to 0.1 into 125 microsecond. So tau is 12.5, and after getting tau, I am going to substitute this tau value in the bandwidth formula. So after substituting this tau value, I got the bandwidth as 40 kilohertz. Okay. So in pulse width modulation, the width of the pulse varies in this method, but the amplitude of the signal remains constant. So here the three parameters. One is the amplitude, width, and position. Here the width is varying, the remaining two is going to constant. So the width of the pulse varies, but the amplitude of the signal remains constant. So we can call as this one is pulse width modulation is also known as pulse duration modulation. So here you can see the carrier pulse. Why? Because this is pulse modulation, analog pulse modulation. So the carrier is in pulse form, but the message is in analog form. So here you're having three varieties of pulse widths are there. A, B, C. Three pictures you can see. So the three variations of PWM. One is the leading edge of the pulse being constant. The trailing edge varies according to the message signal. So here the leading edge of the pulse being constant and the trailing edge varies according to the message signal. So that is the first one. So here the picture A is first one. And second one is the trailing edge of the pulse being constant. The leading edge varies according to the message signal. So here you can see in this picture B. So here in picture B you can see that the second one. And the third one is the center of the pulse being constant. The leading edge and the trailing edge varies according to the message signal. So having three variations of pulse width modulation can be available. So for the generation of PWM, here we take a 555 timer. So you know that 555 timer is 8 pin. So here you connected all this going to these pins, but the output is taken at port 3 or pin 3. Okay. So it is basically a monostable multi-vibrator with a modulating signal, input signal applied to the control voltage input. So it is a monostable multi-vibrator and the input signal applied to the control voltage input. So internally the control voltage is adjusted to 2/3 VCC. And externally applied modulating signal changes the control voltage and hence the threshold voltage level. And circuit diagram of this 555 or monostable multi-vibrator. So here you can see the two transistors which are connected and the circuit works as a monostable multi-vibrator and the triggering is given at the base of Q1. So the stable state is achieved when T1 is off and T2 is on. So having two transistors, it is going to present as T1 and T2. So T1 is off. The first transistor is off and second transistor is on. That is the stable state. So the positive trigger pulse at B1 switches T1 is on. So here in this picture we can see B1 is the base of Q1. Here I am giving the positive trigger pulse. After applying this positive trigger pulse, Q1 is going to on. But the stable state is T1 is off and T2 is on. But after applying the positive trigger pulse, the first transistor is going to on. Why? Because we know the monostable multivibrator having only single stable state. So the modulating signal is the message signal and the carrier, and finally we got the pulse width modulation. So pulse width modulated signal. So that is the output of this monostable multi-vibrator. And again the demodulation of PWM. So here we are giving the noisy PWM. Why noisy PWM? Here whenever the signal enters into the channel, that additive white Gaussian noise it adds up, the signal is going to corrupted. So that's why we can call it as noisy PWM signal. That is the received signal which is going to apply Smith trigger, and in this demodulation circuit having Smith trigger, ramp generator, adder, synchronous pulse generator, level shifter, rectifier, and finally LPF, low pass filter, and finally you get the demodulated output. So here also the demodulated output is a message signal. That is a continuous message signal you get it finally. So the received PWM signal is applied to the Smith trigger circuit. The Smith trigger circuit removes the noise in PWM waveform. Why? Because the received signal is a corrupted PWM. So the signal is going to corrupted with the noise. So the Smith trigger, which is going to remove that noise in PWM waveform. The regenerated PWM is then applied to the RAM generator and the synchronization pulse detector. So here we can see the waveforms of these different blocks outputs. Why? Because in demodulated PWM we use different blocks. So first one is a PWM signal, that is corrupted PWM signal, and after getting the synchronous pulse generator output and RAM signal output, and these two going to add, so you get the adder output. After having level shifter, so the level shifter output, you can see that one. So the level is going to shifted, and the output of a rectifier. Why? Because we use a rectifier also. And finally having low pass filter. So the low pass filter, which is going to smoothen the curve, and finally we get the demodulated signal, that is the recovering of the modulating signal. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.